Next, let's move on to team SegVol, led by Yuxin. Yeah, hi Yuxin, could you please share your screen?
Yeah, sure.
Yuxin is a master student at the Hong Kong University of Science and Technology, Guangzhou. He has interned at Shanghai Jiao Tong University and Beijing Academy for Artificial Intelligence. His research interests in vision large language models and end-to-end learning. SegVol is one of the earliest 3D interactive segmentation model in the community, which support point box and text prompts. It is also the ninth highest rated paper in Europe's 2024. In addition to SegVol, I would like to also highlight his another project, M3D, with Dr. Bai. It's a multimodal model for 3D medical image analysis. So again, the code base is very well structured and elegant, allowing to incorporate various large language models and image encoders in a plug and play way. So yeah, without further ado, Yuxin, it's yours.
Okay, thanks for your introduce. Today my topic is about the stand on the SegVol, and well, I hope you can touch here. And there are a lot of details in the SegVol paper, so today I will just go straight to the key parts that hard to understand just by reading the text. Okay, first I will tell you about the motivation of the SegVol. A very typical uniter model pipeline. We have an image encoder, the 3D variety, and mask decoder to decode the mask, and the sliding window algorithm to go through the whole image or whole volumetric. Why we need the sliding window? Because the 3D medical volumetric is so big, the volume is very big, and the model, the memory of the GPU is limited. So we apply the sliding window algorithm on this image, and we get a lot of slices of the original image, and we can input them into the uniter, and we get the PCO results, and we connect them together, and we get the final result. But for our task, for our interactive segment task, for example, we get a prompt here, and if we still apply the simple sliding window algorithm, for example, we get a window here, we do not have the driving signal from the user, because in this scope we do not have any prompts. So for our interactive model, that's a problem. That's our motivation to prompt the SegVol to solve this problem. Very similar to the uniter, we have a 3D variety and our image encoder, and we have the mask decoder. And we just following same, we get the prompt encoder to encode the prompt like points and boxes. To improve or to solve this problem just presented before, we propose the zoom out, zoom in algorithm. The left big figure is a whole picture of SegVol's structure. It has two parts. The upper part is a core part of the SegVol. You can see the yellow part is the model. We can input the volumetric input and some prompts, and we can get the results. The input is a fixed shape image and some prompts, and we will get the same shape prediction from the model. So how can we conduct the zoom out zoom in? Is a lower sub figure. We have two branch. The upper branch is the zoom out branch. First, we have a very big volumetric input, and we can resize it to this fixed shape, and we can input it to the SegVol model, and we get initialized or very preliminary results here, and we resize it back to its original shape. The resize operation will lose a lot of information, but we still can get very coarse results here. And based on these results, we can get the result interesting, and we can get something like a pseudo label here. And based on this information, we can get into the zoom in branch. In this branch, we can apply the very easy sliding window method on this region of interesting, and we just like the previous slides, we get a lot of slides here, just same like here. But what is different is that we have some generated prompts based on this prediction here. It's coarse, but it's something accurate. So based on these prompts, we add the slice input, we can get a slice of window predictions here, a lot of predictions, and just like the slide window method, we can rebuild it to the original shape and backfill it to the original prediction. We know that in this case, we do not lose any information like the resize operation. We just use the original resolution here, so we can get a very good performance. Make a recap here. In the global branch or the zoom out branch, the model's input is a resized global volume and the global prompts. The output is a resized prediction. And in the zoom in branch, the model input is a lot of local volumes generated by the sliding window, and the rule-based generated prompts based on the first prediction. And the model's output is a lot of local mask predictions for each volume, and we can build it together as the original shape. Okay, so that's the key point is to solve the problem of the limitation respective fail. Here I will go to some code details about SegVol to help you to modify it to make it better. So I will handle it first from the inference part, because if you can handle the inference part, you can figure out the whole map. Here first, we need to know the input and output of the SegVol. We just said that it's a fixed shape image as prompts, and we get the fixed shape predictions. And so in the zoom in branch, we get the shape like this, and in the zoom out branch, we get the same shape, just the resolution is different. Okay, from the dataset provided by the code bench, we have the NumPy images, and we can make some normalized pre-process, and we get the original size images, and go through some transform. You can find the same name in the code. So you can use this as a map to find the logic in the SegVol code. Go through the transform for test, we get the resized image, just the image here, the resized image. And just same, we have boxes, and go through a build binary cube method. Why do we not use the box directly? Because we have some resize operation, crop operation, slide window operation. If you use the box coordinate directly, you will involve a lot of coordinate transformation that's very complex. So we want to make it easy way, just like to resize or crop the images. So we build the boxes to a binary cube. It's just like an image, but for example, the 0 background and the 1's foreground. And it's easy to make the transform operations. After we build this binary map, we get the box cubes. I call it box cube because it's just like a cube in the zeros, one cube in the zeros. Okay, the cube is also the original size and also goes through the transform for test. We can get the resized box cubes. It's just resized. Like here, it's a prompt and have the same size of the resized image, and the SegVol can input them, can accept them because they have the resized shape, and now we get the resized predictions, just like here, the resized predictions, and we use the 3D interpolate operations, and we get the original size prediction mask, just like here. You can evaluate based on these predictions. You will get just social results, but following the zoom in part, we can refine it very impressively. Okay, now we get the prediction masks in the original size, and we can get the region of interesting coordinate, just like here, and use this coordinate. We can make some crop operation, crop the images and crop the cubes, the box cubes. And we get the ROI images and ROI cubes Okay, just like here, our images. And go through the sliding window disassemble parts, we get a lot of the slices or images and the slices or cubes. That also shows the advantage of this operation. We can just apply the original sliding window operation on these images, image-like prompts. Okay. Now we have these slides and the prompts, and they can also go through the SegVol because they also have the fixed shape like here. And after that, we get the predict masks. We call it zoom in masks, just like here. This predicts masks. And we use the original sliding window example codes and rebuild them to the RL pre's, just like here, and just backfill it directly back to the pre's mask. That's how we get the original fine grade prediction. Okay, that's how the SegVol infer case. It's maybe a little complicated in the paper, but it's very directly idea. This part is about the zoom out part. We process the resized images and get the resized predictions and interpolate it back to the original size. And this part is the zoom in part. We use this coordinate to get the most important part because we want to reduce the cost of inference. So we just focus on the meaningful parts. Okay, after this operation, we get the refined predictions. Okay, after we know how to infer a case, it's very easy to understand the training process of SegVol. It's a very simple training method. It's add-to-add method. In this figure, you can see there are two parts that SegVol need to handle. First, the resize images and resize prompts, and the second part is the original resolution parts. So in the training process, we have two branches to train the model to be able to handle these two situations. First, we pre-process them, just very normal operations, normalize and binary, and here we applied one of the transform, resize or crop. If we apply the resize operation, we will get the zoom out data. And if we apply the crop operation, we'll get the cropped data. And the after part is very same. For the resize part, we generate some prompt and input the model and get the predictions and use the dice loss and PC loss. It's the same to the zoom in part, input to the model and get the predictions and use the supervision to get the loss and train the model. So that's very easy for training. It's very easy to train a SegVol. That's a zoom out ability, and the down part is about the zoom in ability. So here I have some suggestions for how to improve the SegVol for this task. First, I think just like Mask just taught, show the figure of the SegVol performance. Maybe SegVol is some of the degrees weak in the refinement because in the training process we do not involve any refinement process training. So the first suggestion, I think you have to do this operation. You need to treat the SegVol with a refinement process to support it able to do this task. And the second suggestion is, I think that's what I really want to do, but I have no time. So I think you can try it. You can add a new vision encoder in the SegVol. You can see here, the SegVol handle two situations. The zoom out situations is transformed by the resize operation, and the zoom in situations is transformed by the crop operation. But we applied this operation all in the same VIT, 3D VIT. So maybe here's some domain gap in these two situations. If you can add a new vision encoder for one of these situations, like the zoom out situations, you can boost the performance. But you need to know if you add the new encoder, maybe you need to do some pre-train like MAE or simple MAE, something like that, to achieve a better convergence and performance. And the third suggestion, I suggest you to add some REST connection, just like UNet, because the original SegWall just use the high-level tokens to decode the mask. In this structure, you can see that we get the mask embeddings from the attention outputs and we input it directly to the mask decoder. But there is no connection between the layers in the image encoder and the layers in the mask decoder. So you can make some like a control net or something like the UNet connection between the image encoder and the mask decoder to strengthen its ability to segment the small objects. Okay, and further, maybe the REST connection can support a heavy decoder. Now the SegVol just have a 2-layer transform decoder following SAM. So if you have a REST connection, you can just make it more heavy, to achieve better performance. And I will show you some code here. I built a repo for the
Sorry,
SegFM.
we are a little bit out of time. Yeah, could you please
Okay.
wrap up?
I will
Yeah.
add it in
Thank
seconds.
you.
Okay.
Thank you.
That's the final part, and the SegWall have 2 attributes: the good performance and easy to modify. Here is a paper link and the code link, and that's my emails. You can email me freely. Okay, that's all.
Okay, thank you so much.